Hello and good afternoon, good evening, good morning, whenever you're watching this. This is Mr. Hill with Metallic Bonding. We're going to continue our series of bonds of the pure materials, compounds, and mixtures. Metallic bonds in itself are consisted of attracting the free floating valence electrons from the positive charges of a metal ion together. Also, the positive metal ions are like a sea of electrons, and the electrons are shared amongst every metal ion. So, if you can imagine, it will look something like this here. The atoms of the metal itself stays in one place, but yet the electrons move freely around the ions or even atoms of a metal. So, as in this picture right here, we see the electrons, we see the metal atoms, and then we can see the sea of electrons, and how that sea is the busyness of electrons. Those look like a baking pan for cupcakes of some sort on this right hand side image right here. All right, so here's a breakdown of metallic bonds and properties. So therefore, it occurs, first of all, bond formation is when the electron, that's what the E with the negative sign right there represents, is that the electrons are delocalized amongst metals. And delocalized or delocalization means that they are freely moving around or away from atoms. They can flow. So this is one clue as to metal being able to conduct electricity, because electricity is the flow of electrons. And therefore, we'll see very clearly if or how metals conduct electricity. So the type of structure, sea of electrons, physical state is solid at room temperature predominantly. Melting point is very high. Soluble in water, no. And that's because of the fact the solubility is not contingent upon an ionic bond of some sort. Ionic bonds are between a metal and non-metal. When you have metal and metal, you get something different. We'll talk about that shortly. Also, they do conduct electricity, and also the properties is that it's malleable, ductile, and lustrous. And we will talk about those as well. So the structure of the metal is that it has a fixed position, the metal ions, like a crystal lattice. So you may recall from before we talked about crystal lattices dealing with ionic structures. Well, metals have what's called a metal lattice, and it has a lattice that is similar to a crystal or crystalline structure, and therefore the bonds results from the attraction between the free moving electrons and positive ions. So the attraction, again, is dealing with the positive ions or the cations, if you will, and it's the moving of the free moving electrons. So here's the C itself. Here's another image of that as well. And the gray spheres are the atoms or the ions of the metal, and the little red dots that like this one around the water are the freely moving electrons. And they call it the sea of electrons because these atoms of metallic structures are actually embedded or just basically overran with these electrons flowing around. All right, the conductivity of it, as far as metals, is a good conductor of heat. Heat causes electrons to move faster. So that's bumping or just pushing. In other words, there's a force that's being acted upon electrons. And when that happens, the protons transfer the heat. So heat is transferred from the protons, and also by the movement or the increased movement of the electrons itself, because it's collisions. Word from another word for bumping is collision. So the electrons collide with each other. That creates some friction, which creates heat, and the heat is transferred by the protons. Metals conduct electricity because of free flowing electrons. When you have a flow of electrons or a sea of electrons, that means electrons can carry a charge from one to the next. So when you have the force acted upon it, which would be the current, if you will, of a wire or electrical uh, force acted upon the sea of electrons in the metal, it can therefore conduct electricity, conduct a signal, if all those type of things. Moldability means that when you apply a force, that the metal actually can move a new location. That means you can stretch the metal out. Metal can be stretched out. It can be beaten until it starts to flatten out. And that's because the ions or the atoms inside the metal itself starts to actually slide from one location to the next because of how it has that lattice structure. It allows it to break off and slide. Ductility or ductile states of metal, if you will, deals with it can be permanently deformed or it can be shaped into. So deformity or permanently deformed or something said to be deformed in science, it means to be shaped into something, to look into something, if you will. And it can do that without fracture. Fracture means you don't have the structure being riddled with cracks in it that will make it brittle or make it where it does not conduct heat or electricity very well. And all metals are ductile at elevated temperatures. So even as you start to go from room temperature up, even towards its melting point, it can still be ductile even then, even if it's soft. And right here we have a picture of ductility. So this is a piece of copper metal that's being wedged into like a mold injector of some sort for a wire and is go back as being made into a wire. Then on the opposite side here, we have the forces acting on the metal, and let's see if electrons make it where the metal could be stretched out. It can be stretched out. It can move out of one place to the next. So it talks about the metal cations and the sleeve electrons, if you will. Whereas somebody else, like ionic crystals, do something like that, is going to create a, a new crystal itself, or it's going to basically break off. It's not going to have the same effect as metal, if you will. So multiple inductivity looks like this. You have an external force acting on the electrons. Let's see electrons. So you have positive charged particles, and that force begins to interact and make it where you can have the ductility. So mobile ease allows atoms to slide by like ball bearings, if you will, in oil. Also, the crystalline structures here, metals are arranged very compact and orderly patterns. And so the metals itself follow again like a crystalline type of structure and pattern where it's predictable, repeatable over and over again, as we can see right here. And I do believe this may be, I want to say some zinc or nickel, if you will. Well, I'm not sure what it is, but it's definitely, I'm not sure what type of metal it is, but it's definitely sure it's metal. High melting point. Generally, high melting points indicate that the melting bonds or metallic bonds are quite strong. So therefore, we talked about this before about where if you have a strong bonding, where in ionic bonds, for example, the bonds itself has no space for electrons to move or operate. And because of that, you have to wait for things to be separated in order for it to conduct electricity. And how those bonds are very strong because it requires a high temperature. So the higher the temperature, that's because the stronger the material is that you're trying to shape, mold, do something with ductility, whatever the case is, what you need it for. So therefore, melting points increase with the increase in the number of available electrons to that sleeve electrons is what it's referring to. And since there's a greater attractive force between the cations and electrons, high density. High density is that where most metals have high density because metallic lattices are closed, packed closely packed. So there are similarities in ionic structures as to metallic structures. I said ionic is not ionic, it's ionic structures are very close in structure of metallic structures where you have things packed closely together. And because of that, it makes it where the density is going to be higher per square foot, per kilometer, per whatever they try to measure it by. All right, here's the virtual assignment. Go ahead and do the metallic bonding assignment. You get 10 tries for it. If you have any questions, contact me through Schoology or my email, and we can go from there. I just want to tell you thank you very much for watching this video.